So it turns out that X bar and R charts are just one of the many kinds of charts that we can build. So in this chapter, we're going to talk about charts for variables data. So the first chart to talk about is X bar and S charts, which are standard control charts just like X bar and R charts. But instead of using the range, we use the standard deviation. And you choose to use this kind of chart when you have enough samples that you're grouping together. So generally the rule is if you have more than 12 things in a group, then you should use standard deviation instead of range. So it turns out that there are a lot of situations where grouping the data just really doesn't make sense. It may be that our samples come too far apart, or that there just really isn't any rational reason to group. So what we're really talking about is times when it isn't just that our groups need to be rational, it's that there is no rational reason for grouping. And if you group when there's no reason to group, you're going to hide assignable cause variation. So in these situations, instead of grouping, we're just going to make a chart from the individual readings. So these charts are called individuals and moving range charts. We still need some measure of variance. But instead of grouping things, we will use a moving range. A moving range is dependent on k points, and we make a sequence of them. So we take the first k points, starting at 1, and make the range of that. And then we start at the second data point and use k points and make a range from that, and so on and so forth. Often we make these charts with k equal to 2, which means that the range is just the absolute value of the difference between two sequential points. So we use individuals and moving range charts when grouping doesn't make sense. But if you can group, you should, because these are less sensitive than X bar and R charts. Zone charts are a variation of those individual charts. In zone charts, we make the individuals chart, but we give each point a score based on how far away from the center line it is. So the amount that one data point adds to our sum is between 1 and 8, and it depends on how far away the point is from the center line. We keep a running sum of that data and reset the sum anytime the plot crosses the center line. If that sum ever gets to 7, the process is changed or is out of control. When I was reading this, I found this chart to be very confusing, and after a little while I figured out why. The scale on the right is not to scale, so the tick marks should be evenly placed from the center line, but they are not. And then it is being labeled by the weights that are given, like the scores that are given to points in that area, not by what the actual scale is. So I posted a paper explaining these charts better that helped me clear up what I couldn't understand from reading our book. There's a technique called pre-control that we can use really early on when we don't have very much data. In this case, we set the limits based on the specification limits, not control limits. So we take the distance between the specification limits and divide it into 4 sections. The 2 sections around the center line are green. The 2 sections between that line and the specification limits are called yellow, and outside of the specification limits are red. We start by taking 5 samples. If they are all inside the green area, then we consider the process to be in control and go from there. If they are not in the green area, then the process is out of control, and we need to reduce the assignable cause variation. Once we find that we're in control, then we take 2 samples every now and then. And depending on where they fall in the red, green, and yellow zones, that decides whether things are in control or out of control. Remember, the purpose for this is to be able to detect whether in control or out of control very early on before we have enough data to set real control limits. Up to this point, all of these individual charts have been using the average moving range. as a measure of variation. However, one or two outliers can skew the average pretty easily. So in times when you can't group and you're worried about outliers having too much of an impact on your limits, you can choose instead to use the process median in place of X bar and the median range in place of R bar. This will mute the effect of those outliers. Now, if we have outliers, an individual's chart will react really quickly because a single point will be able to make you look out of control. When we were grouping, outliers were muted by the fact that they were part of a group. So maybe we'd like to be able to do that even when we can't have rational grouping. So if there is no rational reason to group, but we would like to mute the outliers a little bit, what we can use is a moving average, just like we used a moving range. When you're using a moving average, all of the points that you're averaging together are equally weighted. But sometimes people think that more recent readings should give more, or possibly less, weight in the moving average. In this case, you would use exponentially weighted moving averages. This will be a series of moving means, but these are weighted means. And essentially at each point, what you do is multiply the new data point by a factor and add it to 1 minus that factor times what you had used before. And that multiplier is between 0 and 1. And the book says it's usually 0.2, but I'd have to think about why would 0.2 be a magically wonderful number for that. So if I use 0.2, essentially what that means is 20% of my new number is going to come from the most recent piece of data that I've seen. And 80% is going to be a function of all of the data that I've seen in the past. So sometimes one individual may give multiple samples. We may want to test a component and see how its behavior varies over a period of time. Or we may have a cylindrical rod and want to be able to test its width at a variety of different points. In these cases, a multivariable chart might be useful. Essentially, in these charts, each reading is plotted as a vertical line from min to max, and you can mark where, if you took more than 2 readings, you could mark where all of the individual readings were in that vertical column. In these kinds of charts, it's easy to see things like a lot of in-sample variance or a lot of between-sample variance, a trend, or when there's a particular pattern to where a bad reading is coming from. Sometimes in an individual's chart, instead of plotting the actual values, we plot the difference between that actual value and either a target value or a historic process mean. We can then use a moving range of n equal 2 to estimate the variance, and this gives us a chart that is centered on 0. Now remember, in all of these things, we need a chart that is looking at the mean, and we also need a chart that is looking at the variance. In this case, you would use a moving range chart. And remember that you always check the range chart before you check the mean chart. Z-charts are like difference charts in that we're centering them around some target or historic value. But instead of plotting the difference, we're going to scale that difference by the process standard deviation, which is going to give us a z-score, assuming an underlying distribution. And then the outer limits of the chart will be at plus or minus 3, because that would be in units of standard deviation. Now, most of the time, the center line on an individual's chart is the grand average calculated from the data. But if you want, you can make the center line be the target that you're aiming for. But then you have to remember that that means your action and warning limits may not be symmetric around that center line. This chapter is a really good example of the fact that these videos do not replace reading the book. I focused in this video on how you pick which chart to use, not the mechanics of how the charts are calculated. You certainly need to read the book to see that part of it.